webinar of today, which is organized by OGS and Sotacarbo in the frame of the ECCSELERATE project. ECCCSELERATE project is a project led by ECCSEL ERIC. ECCSEL ERIC is the European Research Infrastructure Consortium. If you want to learn more about the ECCSELERATE project and ECCSEL ERIC, you can visit our website www.eccel.org. I'm just going through the webinar, today's webinar, which is the 5th webinar we are organizing in this in the ECCSELERATE project. The title of today: calcium looping, a process to industry decarbonization. We will have some keynote speakers from ENEA and LEAP, and we will have a very nice chair, which is Robert de Kler from TNO. I'm passing the floor to the chairs of today, so I'm passing the floor to Robert. Robert will introduce both Maurizio Spinelli from LEAP and Stefano Stendardo from ENEA. Robert, the floor is yours. Please start the webinar.
Yes, thank you. So I'm happy to introduce both speakers. I will start with the first speaker. That will be Dr. Maurizio Spinelli, and he holds a PhD in Energy and Nuclear Science and Technology from the Politecnico Milano. His main research interest is in conceptualization and thermodynamic analysis of high-efficiency CCUS process for the reduction of the carbon footprint of major industrial sectors. And since 2011, he contributed in several public and private research projects by developing process simulation techno-economical evaluations of CO2 capture systems. A specific focus of today's talk will be on calcium looping, also in conjunction to the Clinker project. So, and before I think we will first go into this keynote speak, and then I will introduce the next speaker. So, the floor is yours, Maurizio.
Thank you very much. Hello, everyone. Thank you very much, Michele and Robert, for the nice introduction and for this great opportunity. From the summary here, we have the summary of my presentation. Before going to the main calcium looping topic, I will spend a few words about LEAP and the CO2 box. So LEAP stands for Laboratory of Energy and Environment of Piacenza. It is sited in the northern Italy, and it is a research center that provides consultancy, technical services, and research activities belonging to 4 main topics. So the first one is waste to value, the second is low carbon technology, which is the area I belong to. Then we have a smart energy system and emission and air quality area. So LEAP researchers are actually involved in several activities related to both modeling and experimental works. In particular, experimental efforts are currently carried out either on site or in one of our 2 laboratories. We have 2 laboratories. The first one is the heat box, which is used for assessing boiler performances. The second one is the CO2 box laboratory, which belongs to the ECCSEL network actually. And this is a test rig for the assessment of the thermodynamic properties of CO2-based mixtures. So LEAP carries out experimental campaigns to measure single-phase pressure, temperature, density properties and vapor-liquid equilibria for CO2 mixture. So this laboratory is really related to the CCUS world, as it can be used for characterize the CO2 mixture properties, giving essential information for the transport, utilization, and storage steps. So this is a screenshot taken from the ECCSEL website, so you can access this tool if you want to contact us. But let's go to the main topic of my presentation, so the application of calcium looping technologies in a cement plant. So as probably some of you already know, calcium looping is a promising, very well proven carbon capture technology. So it is a regenerative process which takes advantage of the capability of a calcium oxide sorbent to combine with CO2, forming calcium carbonate. This happens by means of the carbonation reaction, which happens at high temperature in a dedicated reactor and produces also heat. Then, after the capture process, the sorbent must be regenerated in a second reactor, the calciner. The reverse reaction is the calcination, so is endothermic, and all the heat required for making this reaction is provided by the oxy-fuel combustion of coal or other fuels. In this way, at the outlet of the calciner, we have a CO2-rich stream gas ready for further purification and sequestration or usage. Characteristic of this process is that we require a continuous sorbent makeup and so a corresponding sorbent purge to keep, for two reasons mainly, to keep a higher sorbent reactivity and also to avoid the buildup of inert species that are introduced in the system, for instance, with the fuel, like ashes. So why using calcium looping in cement plant? Because of this calcium oxide purge, because the sorbent is the same, originates from limestone, which is the main raw material used for producing clinker and cement. And this calcium oxide purge could be exploited for clinker production, decarbonizing indirectly this industry. So the calcium looping process can be applied to the cement industry in two different configurations: the tail end and the tail end calcium looping and the integrated calcium looping. Let's start with the integrated concept. So in a conventional cement plant like the one depicted here, you have the CO2 is generated by different processes. So first of all, we have the CO2, which is related to, which can be named as a process CO2 emission because it is related to the calcination of the material. So it doesn't come from combustion, but from the process itself. And this is almost entirely generated in the calciner of the cement kiln, which is the most energy intensive section of the whole cement production process. Still in the precalciner, we have also another arrow, so the orange one, which is the CO2 generated from combustion within the precalciner, which is needed to sustain the calcination. And then we have a second contribution coming from combustion, which is the minor one, and which is generated by the main burner that we have in the rotary kiln. And this burner is required to, is needed to bring the clinker to the raw material to very high temperature and to produce clinker. So how can we apply the integrated calcium looping concept in a cement plant? First of all, we have to switch the precalciner to oxy-fuel combustion. So the precalciner plays in this concept the double role of feeding the carbonator for CO2 capture and also the rotary kiln. So a fraction of the sorbent produced, a fraction of the material produced by the calciner is fed, is used directly for producing clinker, and a fraction is recycled to the carbonator. So in this way, we produce at the calciner outlet a CO2-rich gas. So we get automatically rid of the two main CO2 streams of our reference case. The residual stream is coming from the rotary kiln and is captured by the carbonator, which plays the only role of capturing this final, this residual amount of CO2. So the main peculiarity of this system is that the sorbent used for capturing CO2 is the same material used for producing clinker. And since this material has a very small particle size, from 10 to 20 micrometers, we have to use entrained flow reactors, which is a different technology from the, let's say, the conventional fluidized bed system considered for the calcium looping process. So in the tail end case, the tail end configuration is more simple. The calcium looping, the CO2 capture process is placed downstream the clinker burning line. So it is actually an end of pipe application where the carbonator treats all the flue gases exiting the cement kiln. So all the free arrows that I showed before. Again, also in this case, the calcium oxide ridge purge produced by the calciner can be used as raw meal for feeding the cement kiln. The higher is the makeup within the calcium looping process, the higher is also the integration level between the capture process and the system. So since this system is, let's say, the more conventional calcium looping one, it is based on circulating fluidized bed reactors. And so for this reason, the particle size is higher than the size of the conventional cement raw mill. It's 1 order of magnitude higher. So for this reason, the purge, the sorbent purge, before being fed to the preheating tower and to the kiln in general, it has to be milled in a cement raw mill at low temperature and then heated up again within the kiln process. So one feature of all the calcium looping process is that their application involves additional fuel consumption. But the advantage of this capture process is that the heat can be recovered at high temperature because the carbonation happens at 650 Celsius degrees. So we can exploit the high operating temperature of both the reactor actually for producing valuable steam and electricity. So in our simulation works, in general, we optimized the parameters of the integrated steam cycle and also the structure of the heat exchangers network to maximize the electric efficiency for all the configuration that we tested. In general, both the tail end and the integrated calcium looping configurations were simulated in the SENCAP and the Clinker European project, exploiting both 0D models developed with commercial softwares and coupled with more sophisticated one-dimensional routines developed in, for instance, in MATLAB for the simulation of the calcium looping reactors, both the reactors, the tail end one and the fluidized bed system and the entrained flow configuration. Here, just as an example, you have the resulting capture efficiency for the entrained flow carbonator as a function of the reactor length. This has been calculated by a one-dimensional model developed in MATLAB and capable of solving mass, energy, and momentum balance. So as you can see, in order to achieve a significant CO2 capture efficiency, we need a very long reactor, and this is mainly due to the high superficial velocity that we have in entrained flow systems, up to 15 meters per second, but also for the kinetics of the carbonation reaction. So simulation results of one-dimensional reactors models and steam cycle, the optimized steam cycle, were imported in the overall zero-dimensional model, which reflects the scheme here presented for the tail end and the integrated car, to obtain the final performances. Without going into the detail of the assumptions and the configuration of the two schemes, we can skip to the results, showing the three main KPIs that we can use to characterize in general these two systems. So the first KPI is the equivalent primary energy consumption, which takes into account both the direct fuel consumption within the cement plant, equipped with the calcium looping system, but also the indirect fuel consumption or the fuel saving due to the fact that the system exchanges electricity with the grid. In some cases, it imports electricity. In some cases, there is an export of electricity to the grid. The same logic in the second KPI, we have the same logic. So this is the equivalent CO2 emissions, which follows, which takes into account the contribution of the indirect emissions or the avoided emissions due to the electricity import or export. And finally, we have the SPECA index, which is the main parameter used to characterize the performances of carbon capture systems. And as it indicates, the primary energy required to avoid the emission of 1 kilogram of equivalent, in this case, CO2. Okay, in this table, we have the main results of the configuration that we envisaged. First of all, we can see that the two tail end configurations features a steep increase in the fuel consumption compared to the first column, which is related to the cement plant without capture. And this is mainly related to the low thermal integration with the host cement plant, and also to the effect of the double calcination. Indeed, each CO2 molecule which is captured by the system, by the tail end system, experiences a first calcination in the cement plant calciner and a second calcination in the downstream calciner of the calcium looping facility. And this is a penalty for the system. On the other hand, the higher is the fuel consumption, the higher is the thermal input. The higher is the thermal input and the fuel consumption, the higher is the electricity that we can produce by recovering the heat from the CO2 capture system. As you can see, for instance, in the tail end, in the first tail end case with a 20% of integration, we have an export of electricity. As for the equivalent CO2 avoided, we can see that all the systems approaches 90% of CO2 avoided. And as for the SPECA is concerned, the best value is given to the integrated calcium looping. As for the economics, in this chart we have the breakdown of the cost of CO2 avoided, which is around which spans from 52 to up to 58 euro per ton of CO2 for the configurations here envisaged. As you can see, even if the tail end options take advantage of the revenues related to the power export compared to the cement case without CO2 capture, the difference in the overall cost of CO2 avoided from the tail end to integrated one case is very low. So the reason of this is again related to the higher efficiency of the integrated CALS concept. So in a general comparison between the two CALS processes, we can say that both technology are promising in terms of efficiency and cost of CO2 avoided. In particular, the tail end case has a good perspective in terms of retrofitability, technology maturity, and capture efficiency. But it has the inherent disadvantage of the double calcination discussed before, which gives to the process an energy penalty. For this reason, the integrated options features a higher thermal efficiency, still with promising capture rates, but on the other hand, it requires the introduction of a different kind of reactor, which is currently experimentally proven in the Clinker project. Okay, so let's have a quick overview on the Clinker project, which is an Horizon 2020 project coordinated by LEAP. And the ultimate Clinker goal is advancing the integrated calcium looping process for CO2 capture in a real cement plant. In particular, the facility selected for this purpose is a Buzzi Unicem cement plant located in Vernoska in the northern Italy, close to Piacenza. So besides working on the main topic, so the demonstration of the CO2 capture systems, we are also making a lot of efforts in the experimental activities, process simulation, and optimization activities. We will also test and validate the CO2 utilization for the mineralization of inorganic material, which can be considered as a valuable storage option. So here we have some general information about the project and the consortium. Clinker takes advantage of a really competitive and skilled partnership composed by cement industry players, technology providers, research institutes, and university from the whole Europe. So the activities in the first 2 years were dedicated to the design of the plant and to experimental campaigns carried out in specialized laboratories to validate the performances of cement raw mills as CO2 capture sorbents, and also modeling activities. Still in the first period. Indeed, the simulation activities supported all the design phase, providing mass and energy balances for the pilot plant, but also fluid dynamic computations. So simulation are being used also to improve the full-scale performances, optimizing other sections of the plant, such as the cryogenic purification unit. On the left, you have the structure of the work packages. Okay, here we have the project, the original project timeline. The first period, again, was dedicated to engineering activities. We produced, AKN produced hundreds of drawings and also tens of flow sheets that were continuously revised. Then after this, there was the plant erection, and then due to some technical delays, which were mainly caused by the pandemic situation, we asked for an extension of 6 months. So in the end, the project will last 4 years and a half. So let's have a look on the configuration of the pilot plant. This is a TRL7 pilot plant. And as you can see, it looks quite different from the full-scale integrated calcium looping concept discussed before. It is composed by 2 separated entrained flow reactors, the carbonator, the blue, the red one, and the calciner, which is that are designed to treat only a slipstream of the host cement plant exhaust. So the original concept was quite simple, just the 2 reactors basically. But then during the design phase, we have been pretty ambitious in adding components in order to represent as much as possible the behavior of a future full-scale application. For instance, you can see that the carbonator has also the possibility of recycling some of the sorbent from the carbonator outlet to the carbonator inlet to improve the capture efficiency of the carbonator without increasing the energy consumption in the calciner. The calciner is equipped with a preheating stage, again, a riser cyclone preheating stage similar to what we have in a conventional cement kiln. Again, this is for reducing the fuel consumption in the calciner. And also, still in the calciner, we have CO2-rich gas recirculation, which can be used to tune the properties of the oxidant mixture. Okay, we skip to some pictures of the real Vernoska cement plant. Here you can see the full cement plant and the preheating tower before the installation of the integrated pilot. And here we have the rendering of the pilot and of the preheater plus the pilot bolt-on. Some pictures about the opening event that took place in the last October with the main stakeholders involved. Here you have the cut of the ribbon and so on. And here we have a focus on the 2 main reactors. So you can see the red one, you can see the calciner, which is equipped with the 2 different burners exploiting heavy oil as a fuel. We also have multiple oxygen injection for staging the combustion process and having a better control of the temperature profile along the whole calciner, especially in the hot region of the combustion region of the calciner, to avoid excessive particle sintering. On the right side, you have two pictures of the burner and of the screw conveyor, which is used to partially cool down the sorbent and to deliver it to the carbonator. Here you have the carbonator, which is an insulated stainless steel gooseneck reactor. It is a very long reactor for the reasons I explained before. So it is more than 100 meters, and this length is basically needed to ensure the resident time required to obtain a significant advancement of the carbonation reaction, so ensuring to reach a significant carbon capture rates. We also have a variable diameter. Indeed, in the downward section of the carbonator, the diameter is larger, and this is again to reduce gas velocity and to increase the residence time of the particle. Okay, in the bottom pictures, you can see the gas solid mixing chamber, the carbonator cyclone, and the two screw conveyors that plays the role of transporting the sorbent to the kiln for clinker production, transporting the sorbent, the recycled sorbent to the carbonator itself, and also to the calcine, and also to the kiln of the cement plant. So in the end, this is the list of the experimental campaign that we are going to carry out in the very next period. We, as you can see, we will test variable operating condition in the calciner and in the carbonator, especially focusing on the most influencing calcium looping parameters, such as the sorbent excess, or in other terms, the solid to gas ratio within the carbonator, which is a key parameter for both the CO2 capture and the energy performance of the system. So we really put a lot of effort in reaching the stable operation of this pilot, and we are now capable of managing the pilot pressure balances, handling sorbent, stabilize the heavy oil combustion in dust-rich environment, etc. So we are now ready for a complete test, and I'm pretty confident that in the coming weeks we will have the first indications about the real performances of this system. I conclude my presentation showing some of the main dissemination activities that we made along the whole project. And you can also check the Clinker website where scientific documents, deliverables, but also videos are uploaded. So I'm available for questions. Thanks for your attention.
Well, thank you for your nice presentation, very comprehensive overview of the let's say the Clinker project. And yeah, I have not noticed any questions yet, so we go and continue with the next speaker. And if there is a question, just put it in the system and also mention who has to provide the answer, of course. Now I want to introduce Dr. Stefano Stendardo. His background is originally from mechanical engineering with specialization in the energy sector, and is a PhD on modeling of carbon dioxide uptake by particulate solvent in decarbonized energy production. Well, he has been a researcher in the field of energy science and ENEA since 2004, where he was involved in the design of pilot plant CCUS, for which he is now the scientific manager. In 2017, he has been appointed as the reference person in ENEA for activities related to CCS processes. And he is the Italian representative in the executive committee of the Research Fund for Coal and Steel, which supports research projects in the clean steel sector. And recently, 2019, he has been participating as the Italian delegate in the Collaborative Technology Program of the International Agency and Industrial Energy-Related Technology and Systems. So I'm very curious about your presentation. So let's start with your part, Stefano.
Okay. Oh, thank you, Robert, for the presentation and for having me. In this presentation, I will deliver you some results obtained jointly with the Politecnico di Torino within the Sphero project, focus on deep decarbonization of a hard-to-abate industry via inherently circular CCUS project. I will give special focus on steel industry, as the previous presentation was focused on more on cement. At the end of the presentation, I will try to give you all a couple of words about the Sphero project. According to the latest work of IEA, improvement on the energy efficiency for production in heavy industry can deliver a substantial CO2 emission reduction in the near term. But if we want a deep emission reduction in the hard-to-abate industry, but in the longer period, according to IEA, we need the CCUS technology. Here I report the vision of the agency from now to 2017, and as you can see, after a very a quick period from now to 2030 through research and demonstration between now and 2030, beyond 2030, the industry will bring CCUS into action, in particular into the market. CCUS, as you know, is a class of technology which are able to reduce CO2 in existing energy and industrial plants, but also in the future sector where the CO2 are probably are hard to abate, but the CCUS technologies are also a platform technology, a family of technology for clean hydrogen production, or even for removing carbon from the atmosphere in order to balance any potential CO2 which are hard to abate, like in shipment or in aviation and so on. Among the hard to abate industries, as you already know, cement is one of those, along with the steel. Both the industrial sector are responsible for up to 15% of the global CO2 emission. Unfortunately, this emission cannot be avoided with the renewable energy, because this is a process-related emission. As Maurizio said, CO2 is, for example, in cement, CO2 is released from calcination or calcium carbonate in order to produce calcium oxide, which is a raw material for clinker production. But not only cement industry uses limestone as a raw material. Steel industry, in fact, remain the second major consumer of lime in Europe. For example, in 2017, was it estimated that at about 20 million of ton the production of lime, out of which approximately 40% are consumed by the iron and steel industry. So as we are in the age of circular economy, as we know, the idea behind the calcium looping is to use the same material for capturing CO2. So we use calcium oxide to capture CO2 and produce calcium carbonate and release it. For CO2 capture, absorption is the industrial standard option due to the proven applicability with the solvent like monoethanolamine. But unfortunately, this chemical seems to suffer from the presence of oxygen. In fact, in presence of oxygen, amine can form a toxic compound like nitrous amine. So calcium loop seems to be environmental benign alternative to the absorption stripping process. Here I have reported the use of coal for the hydrogen production from coal or biomass. As you can see here, the coal or biomass can be converted in a mixture of CO and hydrogen presence of H2O. Again, this syngas produced from the gasification can be sent to a fluidized bed or to a transport bed, where in presence of calcium oxide, this syngas is converted into hydrogen by means this intensification process. So the water gas shift, which is the reaction of CO with the water steam in order to produce CO2 and hydrogen, can be coupled with the removal of CO2 with the calcium oxide. The net results of those two reactions are the calcium carbonate and the hydrogen, which can be used as a fuel or as a reducing agent in steel industry. And the calcium carbonate can be sent to a calcine in order to close the loop and to start again the decarbonization of the syngas. Let's see how to integrate the calcium loop in steel industry. Here I report the well-known blast furnace and basic oxygen furnaces cycle. In this cycle, solid mixture of sintered material composed of iron ore, composed of coke and lime, are used to feed blast furnaces as flux, but also basic oxygen furnaces in order to prevent any damage of liner of the inner part of the basic oxygen furnaces. The hot metal produced in the blast furnaces is sent to the basic oxygen furnace, where it is converted into liquid steel. The alternative option to the basic oxygen, to the blast furnace, basic oxygen furnace, I mean Bf Bof, is the DRI-EAF, the direct reduced process coupled with the electric arc furnaces. The idea behind this alternative process is to remove the oxygen from the iron ore directly in a solid state. The solid product which coming from these shaft furnaces is sent to the electric arc furnaces, where it is converted again in a liquid steel and then in a secondary metallurgy. Here, conversely to the Bf Bof cycle, in the DRI-EF, there is no need of sintered material, so this process is inherently efficient compared to the Bf Bof, but we still need lime or the lime again to prevent the inner part of electric arc furnaces, but also to form a kind of, let's say, a kind of foamed slag to prevent the damage of inner part, but also to protect the liquid steel from the atmosphere. So lime or the lime play a key role also in this case. Here reported, just for your information, the main parameters used in our simulation. We see iron ore, coke, lime, which we have taken out from this reference. Here I report also the hot blast. The hot blast refers to the preheating of air blown directly to the blast furnaces. Part of the blast furnaces gas leaving the steel mill is used to preheat the air along with some request of methane. Instead, here I report a table of the key parameters for the DRI. For the DRI, we have considered we have considered the Midrex approach. The Midrex approach uses an external reformer for the production of reducing agent to send to the shaft furnaces. We have selected the Midrex because Midrex process is responsible for more than 60% of the global DRI in the last year. Here you can see in more detail the integration of the calcium looping into the Bf Bof, the former cycle I showed you. The first configuration is for the decarbonization of the blast furnaces gas sent to the carbonator. And part of the spent solid coming from calciner in particular is sent to the blast furnaces in order to replace the fresh lime or lime used in blast furnaces. The second configuration instead consider the decarbonization also of the gas leaving the basic oxygen furnace, the second part of the cycle. And we increase also the part of solid sent to the steel mill, in particular to the basic oxygen furnaces. This is the second configuration. For the third configuration, instead, we have increased the percentage of basic oxygen furnaces gas decarbonized up to 60% in order to avoid any external input of methane. Let's say how this configuration will react to the integration of calcium looping. Oh, just an important thing is that thanks to the calcium looping, we can integrate also. This is a very important aspect, a Rankine cycle which can recover the excess heat from calciner, because as you already know, the calciner works at more than 900 degrees, so we can recover a good quality energy. But we also can recover a part of energy from carbonator, because carbonator release in the carbonator there is heat released by the reaction of CO2 with the calcium oxide. Let's see how the energy and mass balance is. Here in this figure, I reported the fuel consumption of inside the steel industry, and as you can see, this is increasing from approximately 20,000 megajoule per ton of steel up to a value beyond 30,000 of megajoule per steel, because we need energy to regenerate the solid solvent. With regard instead to the primary energy consumption, which is the fuel consumption plus the energy needed for the power production, the external power production taken from the electrical grid, this increase from approximately 2,000 megajoule to a value which is below 30,000 megajoule per ton of steel. As you can see, this the total energy is below of the only fuel consumption. This means that with this configuration, we are able to export excess of power from industry and from industry to the power grid. This is a similar aspect that you have already seen in the previous presentation. With regard to the SPECA index, which is the specific primary energy consumption for carbon avoided, this decreases with the increase of efficiency level from configuration 1 to configuration 3, where in the last configuration we are able to recover not only the blast furnaces gas and the basic oxygen furnaces gas, but also the spent solid coming from calcium looping. So a complete integration between calcium looping and steel industry reflects in a lower SPECA analysis, and this in a more efficient configuration. With regards to the economic analysis, we have also considered the specific cost for decarbonization, which is the ratio between the increase in the cost of the total plants to the annual production in terms of ton of steel per year. And we have evaluated also the cost of carbon avoided, which is the ratio of this value to the carbon avoided. As you can see here, we reach, thanks to this good integration between CAL and calcium looping process and steel mill, we have a cost of CO2 avoided approximately to 23 euro per ton, whereas the decarbonization cost is more than 40 euro per ton of steel. The biggest is for the most integrated one. We have completed the mass and energy balance also with carbon footprint based on LCA analysis. The functional unit we have used is the well-known equivalent CO2 emission. So it's a kilogram of CO2 equivalent CO2 emission. All relevant emissions, so methane and so on, are converted, applying so a corresponding factor in order to estimate and calculate its global warming potential. The emission categories we have taken into consideration are the direct emission from combustion process, the emission I have showed you before, the emission associated with the production of electricity, this one, power, and also the CO2 related to the fuel procurement, this one, and the emission related also for the construction of new infrastructure. And we have called this simple infrastructure. As you can see here, you can see also the benefit of the ranking cycle inside this this configuration, because we are able to export here this negative bar. We are able to export the power from industry, steel mill to the power grid. As you can see, also with the increase of integration of calcium looping into the steel mill, we have a progressive reduction of direct emission. In fact, there is the value of 79, 33, and 90% with the increase of level of the integration. Let's see also now for the configuration of the DRI coupled with the calcium looping. We have considered the configuration 4, which take into account the decarbonization of flue gas leaving the reformer, which produce the reductant. With this, we have considered also the 5th configuration, which take into account also the decarbonization of the gas leaving the electric arc furnaces into the reformer in order to replace a small part of methane. And also in this last configuration, we have used the spent solid leaving the calciner directly into the electric arc furnace because of its critical use. Also in this case, we have reported, again, we have replicated the same results, but now you can see also the increase of fuel consumption. This is normal, but for this the primary energy consumption, this increase from 11,500 megajoule per ton to a value which is greater than the greater value of fuel consumption. This means that there is no export of energy from steel mill to the power grid. Nevertheless, the spec index is lower, because for for configuration 4 we have 4.3 megajoule per kilo of CO2. Instead, for configuration 5, which is a more integrated, the most integrated solution, the spec is lower. So it means that the last configuration seems to be very efficient configuration. Again, for the economic analysis, the cost of CO2 increases a little bit. We have more of the CO2 avoided is greater, is more than 60%. And the cost, the decarbonization cost is lower, is more than 24%. Yes. So also in this case, we have completed the mass and energy balance with the LCA. Also, again, here confirm that there is no benefit from there is no export of power from steel mill to the power grid, but nevertheless we have a reduction of the CO2 related to the combustion process. Few words to say that if we want to have even more deeper decarbonization in industry, this is a general aspect, we have to encourage the renewable energy source also in industry, and CAL can help in this regard. In fact, I can offer an optimal solution to collect the solar energy into the calciner with this reaction. Calcium carbonate is decomposing the CO2 and calcium oxide, which is sent to which can store the format, the CO2, in a supercritical approach way in a pressurized tank, the calcium oxide instead in a conventional silos. And then these components can be reused in a carbonator in order to release the heat, and so to feed a classical Rankine cycle with a high pressure, medium, and low pressure. The energy storage system is composed of the calciner itself, but also from the compressor unit, which is able to store in a supercritical phase the CO2. We have approached the integration of this, or say the recovery of the excess heat with the help of the well-known pinch analysis. We have highlighted in particular 3 hot stream, which are the CO2 released in the calciner, the calcium oxide produced in the calciner, and the CO2 leaving the storage compressor. The only key cold stream is the calcium carbonate, which fed the calciner. Similar approach also for the energy release area. This is composed of the carbonator, which releases the heat, and the CO2 storage tank, where the CO2 can where the energy can recover by a train of turbines, so we can recover part of the compressor work. The heat is mainly supplied in these 4 via these 4 exchanger units. We have this evaporization which helps to maintain as constant as possible the temperature inside the carbonator, because this is an exothermic reaction, so we are able to produce a heat, and then the remainder part of heat is released by the CO2 leaving the carbonator in this closed loop, so we can have a superheater, a reheater, and an economizer. the most important feature of the calcium looping as a storage system is the potential applicability also of the district heating network. In fact, for the intercooled decompression of CO2 during the gathering of energy, cooling is, is necessary in order to maintain as constant as possible. Also here the temperature of gas during the compression. So a refrigerant circuit, we have modeled a refrigerant circuit which is able to absorb the heat during the compression and to release the same quantity in a district heating unit. During the recovery of turbine, when the CO2 is released through the carbonator, instead we have the opposite need, so we have to heat the CO2 because the expansion can cool down the CO2 with potential condensation of any droplets. So we need our heating circuit able to heat up the CO2 and absorb this heat in an external volume, so producing cooling. This is just to give you a flavor of the summary. We have published a full paper on that. We see that if we consider in the global efficiency also the heat and cooling district, the global efficiency increases from 40% to 50%. So calcium looping gives also the possibility to be hybridized, to be integrated with the other storage system like mechanical one. I want to complete this presentation to show you the ECCSEL pilot plant. I'm proud to say that it belongs to the ECCSEL Consortium. This is a 500 kilowatt pilot plant. ECCSEL stands for zero emission of carbon with mixed technologies. The aim of this pilot plant is to produce hydrogen with the calcium looping process. The novelty of the ECCSEL is the combination of well-known industrial process like calcination, because we borrow this from the cement industry, but also from the steel. The gasification and the reforming of conventional fuel for producing hydrogen. Here I report the composition of syngas produced by a bubbling fluidized bed. This is, as I told before, is a 500 kilowatt thermal bubbling fluidized bed. And in this reactor, we are able to simulate any composition similar to the gas leaving the blast furnaces or even the basic oxygen furnaces case. So we can replicate the same condition of the gas leaving steel mill. So we can have a figure and an estimation how efficient is calcium looping for the decarbonization of steel mill. Particularly here you can see instead the composition of the gas leaving the carbonator. We have simulated inside this carbonator, which is a bubbling fluidized bed, high 5 meter high with an inner diameter of 1 meter. In particular, in this experimental campaign, we have fluidized 200 kilo of dolomite with gas, with a mixture gas composed of 10 kilogram per hour of CO and 50 kilogram per hour of H2O in order to simulate the water gas shift intensified with the capturing of CO2. And as you can see, this is a very explorative experimental campaign, but nevertheless we were able to attain good results because the gas leaving the carbonator has hydrogen content oscillating between 50 and 60% in dry basis. The remainder is composed of unreacted CO and CO2, which would not be able to, capture because the calcium oxide would convert it into calcium carbonate. This means that we have to add more calcium oxide in order to below the content of CO2. Here, just for your information, I reported another experimental campaign regarding the use of calcium looping as a process for storing in a permanent way the CO2 in a alkaline industrial waste like steel slag, or even the ash from incinerator, because the ash from incinerator, like the ash from the steel slag, have a good component of alkaline, which are able to be carbonated, and so to be used as a storage of CO2. This is a freshly baked results in the Zecomix, because Zecomix is a wider infrastructure. In particular, here you can see the use of cold plasma for converting CO2 in CO and oxygen. This is a very promising technology. This is the last results we obtain in our facilities. The idea is to use advanced as a catalyst assisted by plasma in order to split the CO2 in CO and oxygen at lower temperature. Just a few words to explain the Sfero project. Here you can see the partner, Politecnico Torino, University of L'Aquila, Roma Tre, and Sapienza. In particular, during this talk, I have reported the main results obtained jointly with the Politecnico di Torino inside the work package 1, focus on the evaluation of efficiency and performance of steel and cement industry. So just the conclusion I like to conclude with a kind of graphical abstract. So you can see that the calcium looping is a very flexible process, because you can store excess of energy. You can produce even hydrogen as a fuel, or as reducing gas in steel mill, or for replacing methane or other conventional fuel. You can produce calcium oxide as raw material in cement, or as you can see also in steel mill. Or, but this is another file, is another chapter. You can use all calcium oxide from calciner in a slag lime, just to assist also the direct air capture. So you can also avoid, you can absorb the CO2 with this kind of process, also the CO2 from the air. This is a very challenging aspect, but also the industry world is facing also this kind of process. I think this is the last slide. Yes. So I leave the floor to Robert. To any questions? Thank you.
Well, thank you for your nice presentation. And yeah, what I learned more today is that that also a form of energy storage is in this technology, which is a very interesting thing. We have, I think, in terms of timing, we have one question. So for and that is for Dr. Spinelli. It's about the cost of CO2 capture. I think there should be some more of an elaboration on that, because according to the Annika project by TU Darmstadt, they had lower capture costs. So maybe you can elaborate on that, Dr. Spinelli.
Yes, I don't know right now the assumptions that were made for estimating the cost of the CO2 capture system, so the indirect calcium looping system of the Annika project. So I could not make a straightforward comparison. But what can I see is that the costs that I show were calculated in a previous project, so the SENCAP project, and in my opinion, we had some, let's say, conservative assumptions, both economic assumptions, but also technical assumptions related, for instance, to process contingencies. And also, right now in the Clinker project, we are trying to optimize, and we are quite confident that we can optimize the configuration of the process to reduce. I mean, we believe that we have a great margin for reducing the cost of CO2 avoided down closer to the values claimed by Annika. I give you an example. In the first calculations, we were quite conservative, also in considering the low oxygen concentration in the oxyfuel oxidant of the precalciner, and that is a very important parameter, because if you increase, like we want to do in the Clinker, if you increase the oxygen concentration, you decrease the CO2 recycle, and you decrease the fuel consumption and the oxygen consumption itself. So this is a good point, for instance, for reducing a lot the operating cost of the systems. And then there is also another point which is related to the cost of equipment. In the SENCAP configuration, we considered some correlations for estimating the cost for the construction of an additional preheating tower within the cement plant to maximize and to exploit also the CO2 streams produced by the calciner for preheating the raw mill. And this was unexpected at the beginning, but the cost for building, so the civil works for building that tower were quite high, comparable to the air separation unit or the CPU system. So, but again, these are costs that are really related to the also to the location of the plant. So we have, let's say, some margin to reduce both the equipment cost and also the operating capex and opex.
No, it's very clear, and there's a room for optimization and to improve efficiency, or at least the CO2 cost avoided. Yeah, Michela, I think we are over time. Do you have some last words?
If I may, yeah, if I would have a few quick questions to Stefano and Maurizio. If Stefano is still with us, I would like to ask him, I know that we are running out of time a little bit, but I would like to ask Stefano, what are the bad and the good things of calcium looping technology, and why is it not so extensively affirmed yet at a commercial scale, if you may answer?
Yeah, yeah. The main, the advantages maybe the fact that this is an environmental benign solution, because calcium looping uses the calcium carbonate, which can be a natural occurring sorbent. But unfortunately, if we use calcium looping, a calcium-based sorbent from natural occurring material, this is very poor in mechanical resistance. So a lot of fine can be produced. That's why we are the scientific community are joining the efforts for make a synthesis of material which are hard and make a good mechanical features during the fluidized bed, and even also in transport bed. So this is a very good approach for the because this is not yet adopted in the industry, because Currently, the main challenging option is the absorption stripping options, which is a well-known approach. The industry knows already how to manage the liquid. Calcium looping is not so accepted in the industry because they are more want to use more this liquid solution because it's more you know, they are more familiar with this with these technologies. Calcium looping is more related to the industry, to the calcination. So we have to suggest to the industry that the calcium looping can be used also for producing hydrogen and also for capturing CO2. But now also with the last project, we are in this way. So I think we need a good communication with the industry and to communicate that there is also alternative solution to the liquid stripping and absorption, and even more also a cheaper one, because calcium looping from latest results seems to be to halve also the cost of CO2 with monothalonamine. So this is, I think, the more reason.
Okay. Well, I think as well for the communication, I think energy storage is also very relevant, especially also for the hybrid solution. I think that is very interesting what you showed. So.
Yeah, because calcium looping offers this kind of seasonal storage, because you can store calcium oxide and the CO2 in a conventional way, because calcium oxide can be stored in a conventional silos, and CO2 can be stored in a pressurized cave or in a pressurized tank, and then you can reuse and you can release heat with zero CO2 emission, because the only pollutant is the calcium carbonate, which can be stored efficient, or even you can reuse again in lime production or in cement or in industry, or even you can use also for making the road or like a refractory material.
Yeah, clear. Utilization.
So CCUS or CCS is should be seen as a class of technology which are not in competition with the renewable, but they are complementary with the renewable, in particular calcium looping. So you can use excess of solar energy to store this in an efficient way.
I think Michela is closing down this webinar. I think she wants to thank everybody and the participants as well, also the speakers for the very nice presentations. And sorry for the technical problems, but hopefully next time we do it better. Okay, thank you.
Okay, thank you.
Thank you.
Bye-bye.
Bye.